Okay, let's begin. First, I'll start with a couple of examples because I want to make sure that we know how to do these. Or at least can also see the difference between the two. Okay, so the first function, how would you interpret that? I mean, what does that square mean then? Yeah?
It's saying you're taking the sine of x squared.
Right, so if you see something like this, it means sine and the angle is squared. Versus this one?
That's squaring the cosine, or you're taking the cosine squared of x.
Okay, but how can you think about that?
Like cosine x
Cosine
times
x,
cosine.
cosine x, yeah.
Right, cosine x all squared. And it's important that these two things are very different, right? When you're squaring the angle versus squaring the entire function, those are very different things. Okay, so that being said, how would you differentiate the first one?
Cosine x squared times 2x.
Right, so you have cosine of x squared, which is the derivative of the outer function, times 2x, or 2x cosine x squared would be that one, and that's by the chain rule. Versus that one, how would you look at that one?
You do product rule?
Right.
Or
The power rule.
power, no, chain rule.
You could also do the chain rule. Yeah, product rule could work, just think of it as cosine times cosine. I think it's probably a little bit more complicated if you do it that way. But you could, yeah, just realize there's an inside function inside a square. And so in the same way, you can bring that 2 down, you leave the cosine alone, right? So that's kind of like you're bringing the 2 down, doing the power rule, and leaving the inside alone. And then you multiply by the derivative of the inside, which is minus sine x. So you get minus 2 cosine x sine x. And that would be the answer. Or there's another way to write that. What is 2 cosine x sine x?
Sine 2x.
Sine 2x. Right? Where the angle here is doubled. So I just want to make sure that you know the difference between things like that versus notation. So usually if you see a square like hanging off something, it really means that only the thing inside is being squared. Versus if the square is on the function, it means the entire thing is being squared. So you'll see things like ln of x squared versus ln squared x versus ln of x squared. And it's important to know the difference between the two. In fact, these two are equal. And it should also be noted that the log rule that allows us to bring powers down would only apply to this one and not those. Okay, so I just want to make sure that we're paying attention to the notation in that way. Okay. There was a problem like that on the quiz, but we didn't discuss it in class, so I just want to make sure that we're on the same page here. Let's talk about where we left off last time. So last time we saw the situations in which the derivative does not exist. So one was in the case that we have a sharp corner. And the idea is if our function has a sharp corner, something that looks like this, there is no way, at least no unique way to draw a tangent line that will make it defined, because that would be a tangent line, that would be a tangent line, that would be a tangent line, that would be. There are so many things that can go through this point, but none of them will approximate the curve at that point, because no matter how much you zoom in, that sharp corner is never going to look like a straight line. It's never going to start flattening out. It's a sharp corner. Okay. So that was one situation in which the derivative does not exist. The fancy word for sharp corner is called a cusp. So the second situation was where f is not continuous. So that either means it's not defined, right? There's a hole, or something like there's a jump, right? And again, there's no unique way to write a tangent line here that will approximate the function. The function doesn't even exist there. You can't draw a line if there's no point to draw it on. And versus at a point like this, right? The tangent line can't go here or here. No matter how much you zoom in, those points will also never look like a straight line. So we can't differentiate here. So let's say this is at A, and this is at A. So can't find f prime at A. Same thing here. There's a jump there, there's empty space. No matter how much you zoom in on an empty space, it's never going to look like a line. And similarly, 3, where f has a vertical tangent line. Now, you should remember that functions themselves pass what we call the vertical line test. So you can't actually have the graph of a function being vertical for more than a single point. But you do have functions that have that weird behavior, where yeah, for a single point, they go vertical, and vertical tangent line. So they'll do like this, and then for a single point, they swap and do that. And right here, it turns out zooming in, a vertical line will be the best approximation to the curve at that point. But it turns out that you can have a vertical tangent, but vertical lines have no slopes. But we know the derivative is the slope, right? So this means they have no derivatives. So again, if this here was an axis at A, you could say that f prime of A is undefined. And so I just want to mention an idea that you do want to keep in mind kind of as we move forward. Where is our place? Basically, what a tangent line is, you may come across definitions of a tangent line that do not work. So a lot of times people think a tangent line is just a line that touches a function in one point only, but that is actually incorrect. So I just want to make sure we're thinking of these concepts in the correct way. So the idea here is, what did I want to say? Basically, the best linear approximation at a certain point, which also implies that a function is differentiable find a derivative at a point if it is approximately linear at that point. I.e., for lack of a better phrase, zooming in, it'll look like a straight line. And the slope of that straight line, the particular straight line that it looks like when you start zooming in, is the derivative at that point. And it's possible for such a line to cross a function multiple times, even an infinite number of times, actually. So we can look at a weird example here. That's not where I want to look at. Maybe something like x squared sin x. That'll be a nice one. Y equals x squared sin x. Now, I believe we've looked at this function before. It's the guy that kind of behaves like this. And it just now it turns out at x equals 0, y equals 0 is the tangent line. It will follow the definition, but it turns out if you look at the graph of y equals 0, it will actually touch the curve an infinite number of times. So I want you to think of tangent lines, they're just a great linear approximation. And we're actually going to use them in this particular application. It's one of the most important applications of a derivative, actually. There are a handful of applications of derivatives that are very important. That happens to be one of them, linear approximation, which we'll talk a little bit more about in the coming days. Okay? So we looked at what a derivative is, we looked at some properties and rules of how we can compute derivatives for weird functions. Now we just saw where a derivative would not be defined. Now, what I want to do is talk about another situation in which we would like to be able to find derivatives, but it might kind of be weird doing so in the first case, at least unless you don't know how to do it, which I'm going to tell you now how to do it. And this is called, we're going to talk about implicit differentiation. And this consideration arose because there are two main ways a function can be defined. One is called explicitly. A function can be defined in a manner that we call explicit, or an explicitly defined function. And this is basically when the dependent variable is solved for completely in terms of the independent variable. It's explicitly out in the open, and so it's essentially the functions we've been looking at the whole time. It's like y equals x squared, or y equals x plus 1 over 2, or y equals x e to the x. on the right side, we only have expressions with the independent variable in them. And on the left side, we have the dependent variable just out in the open. It's explicitly defined. I know completely how to determine the dependent variable once I'm given the independent variable, right? So basically, y equals f of x is one way, right? And that's called the explicitly defined function. Another way to define a function, however, is called an implicit way to define a function. Where we say a function is defined implicitly, right? Now that means the definition of the function is perhaps not known, perhaps it's impossible to know in any concrete sense, but we know the definition is implied based on the fact that the equation must hold. So this is like your x's and y's are kind of mixed together. So like x, y equals 1, or x squared plus y squared equals 4, or x squared, y squared minus 3 ln x plus 2y equals 7, right? Basically, you have a situation where you have some rule that has both variables jumbled together equals some constant, right? Whenever you see a function is defined in such a way, it is called implicitly defined. So we can define something explicitly, we can also define it implicitly, right? In explicit, the y value is out in the open, and we can compute it just based on some input value. However, there are times when things are mixed together, and we might not be able to separate the y and just describe it completely in terms of x. And when we do that, it's called an implicitly defined function. Unfortunately, these are pretty common, by the way. Right? Not because, we just want to make things complicated, but a lot of times, just by studying a natural phenomenon, the best way to describe a rule that is describing some phenomenon happens to be describing it in a way where you can't isolate one of the variables. It shows up a lot, and I'll give you one or two examples of that here in today's class. But for a function to show up this way is a very common thing, especially in the sciences. In fact, I'll give you an example from chemistry a little bit later. But yeah, sometimes the best way you can describe some natural phenomena is like this. And in some sense, it's kind of messy to do that. And so the idea is, though, but we'd still want to be able to find a derivative in the explicit case. We still might want to know how fast is one thing moving in relation to the other. That is a very reasonable question to ask. In the implicit case. And I don't know if you can call this a trick, but this is not anything particularly sexy. But the trick to doing this is actually applying the chain rule. Right? So the chain rule is super important for many reasons, but this is one of them. It is the main rule that will allow us to find derivatives in the implicit case. Right? So let's do some illustrative examples here, and then we'll do some actual examples. So the point of these first few examples is for you to see what's happening and why it will be the way I'm going to say it's going to be. Hopefully these examples will make it a little bit obvious. So let's say I want to find some illustrative examples. I'm going to go through these one by one. So let's say I wanted to find the derivative just some function. What if I wanted to find the derivative of some function squared? If I want to find the derivative of x times some function, right? So right here, notice that I'm not even telling you what the definition of the function is, but it shouldn't actually stop you from being able to find a formula for a derivative here. Let's see if there are any other examples. Yes, f of x squared. Maybe I had a few more examples, but I think after doing these, you should be able to see what I'm talking about. Let's just do a couple of these for. Okay. So, how would you describe this guy? d dx of f of x, what can we say that is? Well, let's just write in different notation, shorthand. We call this f prime. Okay? That's our definition of the derivative, basically. What would this guy look like? How do you differentiate that?
2f prime.
2 f of x times f prime.
2 f of x, right? That's differentiating the outer function. And then you have to multiply, right? Let's do it one line down. Then we'd have to, so we'll bring the 2 down, leave the inside alone, then we have to multiply by the inner function derivative, right? That's us applying the chain rule. What would this guy look like?
F of x plus.
Right, so differentiate x, so you get f of x plus
X, f prime of x.
x times f prime of x. Okay. What about this one? I'll throw in one more example. But yeah, what about that one? How would you do that?
Quotient.
What would this become?
F of x minus x times f prime of x over f of x squared.
This one?
Is it 1 over f
1
of x
over f of x times.
times f prime of x.
Okay. So f prime of x over f of x. Okay. What about this one?
Um, 2x times f of x squared
Plus x squared times 2 f of x times f prime.
So notice what we're doing here. Whenever our function f of x is hidden in some part, we just apply the chain rule. One thing you can notice is that every time I differentiate an expression that has our f of x in it, I have to multiply by f prime, because that's what the chain rule says we have to do. Okay, so now, pretty much, if you can get that, you can get implicit differentiation in this sense, because usually we won't be writing f of x all the time. I don't know if it's because we're lazy or what, but usually we won't. Now, here's all we're going to do. We're going to replace f of x with y. That's the only thing I'm going to do. Okay? So here, if I had d dx of y, I might just call that y prime. Okay, not too terribly complicated there. Now what would these expressions look like? So if I wanted to differentiate y squared, what would that have to be? Well, we're literally replacing the f with y everywhere. So this would look like 2y, y prime, right? Because of the chain rule. Here, if I wanted to differentiate an expression that looks like x times y, then I would just apply the product rule. Differentiate this, leave that, plus leave this, differentiate that. If I wanted to find the derivative of x divided by y, well, that's just the quotient rule. It's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. If I wanted to differentiate ln of y, well, this is just going to be y prime over y by the chain rule. If I wanted to differentiate something that looks like x squared y squared, well, that's going to be 2x y squared. Differentiate the first one, leave the second one, plus leave the first one, differentiate the second one. So notice essentially what we're doing here is pretty much every time we're differentiating a function of y, we have to multiply by y prime. And why? Because we're applying the chain rule. And we do this because the y is actually not the x value. Right? It's not the independent variable, it's just some function, and so we can think of it as an inside function. And so whenever we're differentiating something with respect to y, we can look at it this way. There's another way that we can look at it that might be more helpful in other contexts, but for now, you can always think of it this way and it'll work out. But sometimes there's going to be another variable in play, so we'll probably deal with that when we get to it. But yeah, that's basically the idea, okay? So sometimes if your x and your y is mixed up, you can still somehow figure out how to get a y prime in play so that you might want to solve for that. And the trick here is the chain rule. So let's actually now, that I think we got that idea, let's actually apply it inside of a problem. So all you have to do, remember, in this version of implicit differentiation, whenever you see a y and you're finding the derivative with respect to x, it is going to be, you're thinking of the y as some inside function that's there. We can get a little bit more general, but for now, let's start with that. So let's do some examples. Find the derivative of y with respect to x in the following. So the first three examples are important. Let's get through those and then we'll do a few more examples. Okay. So here, you're given expressions where your x's and y's are mixed up, and I want you to find the derivative of y with respect to x. So, A. So we can find the derivative here by, here my x is mixed with my y. I can find the derivative here by just differentiating both sides. And we now know how to find the derivative of something like x divided by y. So what would the derivative of the left side look like? That's your cue. What would it look like?
Y plus x, y, y prime. X times y, y prime. Wait, hold on. It's not chain rule, it's product rule.
Yes.
X, y prime, sorry.
X, y prime. Okay, all right. Derivative of 1? 0. Okay. So now my x's and y's are mixed together. I was asked to find dy dx, however, which is y prime. So now I have an equation where y prime is just one of the factors in this equation. So now I can actually solve for that variable. So this would mean x, y prime would be, bring that over here, minus y. And so that would be my y prime is minus y over x. And I could leave my answer like that. So sometimes when you're differentiating something, you will have the dependent variable as a part of your answer. Now we're going to talk about the consequences and what you need to do in that situation, but this is one way. But let me emphasize something here. But you might have noticed we didn't need it to do this here. We didn't need implicit differentiation. I mean, if you were given that problem and you either didn't know implicit differentiation or you didn't want to use implicit differentiation, how could you have done that problem?
Just subtract the divide by the y.
Well, divide by the x probably.
Yeah.
So you get y. So if you have x, y equals 1, you can get y is equal to 1 over x. Now, always when we're dividing, we need to make sure that our x is not 0. Right? So we divide by x, we have to make sure, did we divide by 0? But we know it's not 0, why? If x were 0, what would happen?
Well, it wouldn't equal 1.
Well, it couldn't equal 1, right? So we know the x is not 0, so dividing by it is a possibility. Okay, so now we could just have this guy. Now this guy we already know how to deal with. This is just an easy application of the power rule. So this would be x to the minus 1, which would give me that my y prime is minus x to the minus 2, or minus 1 over x squared. Okay. Now the first thing I want you to notice is that, so here are some remarks. Was this wrong? Are the answers the same? So that's the first concern I would have. Because I used implicit differentiation, which I applied the chain rule, so it should be a valid way to do the problem. But I get an answer that looks like this. Versus, if I solve for y, did things the old way, I get that answer. Are these the same? Well, it turns out the answer is yes. These are the same thing. And here's how you'd be able to see this. We can that y is equal to 1 over x here. This would mean, if I look at the expression minus y over x, that's just going to be minus 1 over x, which is going to give us minus 1 over x squared, right? So this function, this answer is actually equivalent to that answer, right? It's just that if I'm in the situation where I can know what this guy is, it means that I could have solved for it and actually found the answer this way. So the other remark I want to make is that this shows sometimes implicit differentiation is optional. Sometimes a problem comes to you in a jumbled form, but it's easy to just solve for the y and do things the old way. You don't technically need implicit differentiation. So, sort of overcomplicating things here. So, turns out sometimes implicit differentiation is optional. Now let's look at the second example. Now, this example illustrates another thing. Because I claim here, it's still optional. But it wouldn't be recommended, right? So sometimes you might want to, you long for the good old days, you might want to change something to the old way of doing something, but it's just not worth it at the end of the day. And this example shows that fact. So we could solve for y here. Does anyone see how you would solve for y?
You can factor y.
Sure, I could factor a y out, but there'd
And
be
yeah,
one
you
factor
still
out
have
over
one.
here. And then do what? Does this help? Does that help you solve for y? It's a quadratic. It's a quadratic in y, right? This is like the A, that is like the B, this is like your C. So technically this looks like AY squared plus BY plus C, and I could actually use a quadratic formula to solve for y. So my y would be equal to minus B plus minus the square root of B squared minus 4 times A times C all over 2A. Right? So you could actually solve for y explicitly in terms of x here. It's not a question. And now you can actually find the derivative of this in order to find y prime. But that doesn't look fun at all, and it's not fun. You need like quotient rule, with some serious chain rule in there. And you know, by changing things just even a little slightly, I could also throw in a product rule at you in the same thing, in the same breath. So we could find y prime, but would you want to? So some of you might be wondering from this example, well, is this optional or not? Well, there are times when it is optional, but you wouldn't want to do it even if you had that option, right? So let's do it the implicit way to see how that would look. So if we have 5x squared plus 2xy plus x to the fourth y squared equals 4x cubed, this would mean, so now what we're going to do is we're going to differentiate both sides. What is the derivative of this with respect to x? How would you do that?
10x. Product rule.
Product rule. It's one function times another function. So I do the product rule. So we're going to do derivative of this times that plus derivative of this times that. Differentiate the first one, leave the second one, plus leave the first one, differentiate the second one. Plus, how do you differentiate this?
Same way.
So product rule again, right? With a little chain rule here, because remember the y squared, we're not thinking of that as a single variable, we're thinking of that as some hidden function inside the y. So I'm going to differentiate around it, then multiply by the derivative. So applying the product rule here, I would differentiate the first one, leave the second one, plus leave the first one. Now differentiating the second one is an application of the chain rule. It would look like 2y prime, because my y is a function that's hidden inside there. On the other side, I would just differentiate this, I would get 12x squared. So here I've gone through and I've taken derivatives, and now what you'll notice is I have y prime in two locations here. Now the goal is to solve for y prime, but now it's just a matter of algebra in solving for y prime. I can algebraically solve for this guy. So I could combine like terms here, so y prime, and this is 5x squared plus 2x plus 2x to the fourth y. That takes care of these two terms. By me just factoring out a common y prime, what I'm going to do now is the term without a y prime, move it to the other side. So I have 12x squared minus this guy. That takes care of that. Minus this guy. And that accounts for everyone. And so now to solve for y prime, I can just divide both sides by this. And that will be your answer. Now, yes, that looks messy, but it was a heck of a lot easier to actually do by hand than it would be to do this directly. And second of all, if you were forced to write this as a function of purely x, then all you would do is plug in this expression in every location that you see y, and you can imagine from seeing that expression how complicated it would have been to do this directly. It wouldn't be a very nice time. So there are times when Implicit differentiation is optional, and it's easy to do it one way or the other. There are other times when it is optional, but you wouldn't want to do it. Like in this case, you wouldn't want to do it without implicit differentiation. The third example shows us a very different case. Now, in this example, it is impossible to solve for y. I don't mean it's hard. I very literally mean it's impossible to solve for y. Now, why that is a little bit above our pay grade. In a class like called Abstract Algebra, you'll learn why that is true, which is a math class that's way above this one. We're like 4 or 5 semesters away from that class. But in that class, you'll realize that we know that for polynomials up to degree 5, there is a general formula that can be derived to solve for such polynomials. So for degree 2, the quadratic formula is that formula, and we can have formulas for cubics and 4th powers and 5th powers, but it turns out beyond that, no formula actually exists, right? So there is no general formula for solving a 7th degree polynomial, and most of the time, there is no way to actually solve for it anyway. We can, at best, we can approximate solutions. We can't actually find them outright. Every now and then you'll have a silly little example where you could solve for it, but in general, there is no way to actually do this in general. And for this particular one, you can't solve for y. There's no way for you to actually do it. So if you wanted to do things the old way, you'd spend forever trying to get that to work. But we might still want to be able to solve for y prime here. So, gotta do implicit. Now, with implicit differentiation, we can still do calculus. We can still differentiate here, and it's actually not going to be that tough. Differentiating one side at a time, that would give us 2x plus 7y to the 6y prime minus 2y prime equals 0. And I can solve for the y prime now, just like it was an algebra problem. So y prime, I would factor out 7y to the 6 minus 2, put minus 2x over there. So I'd be able to find y prime. So solving for y itself is quite literally impossible, but finding the derivative, easy peasy with implicit differentiation. We'll stop right there. This is actually a very famous kind of curve. I forgot what it's called. Something has to do with Descartes, but it's actually a function that looks kind of like this. We'll do more examples next time, and I'll show you some real-world examples in which functions like this show up, but we want to be able to find derivatives. So, test next week. It'll be on everything up to here. Okay. So we will be continuing this topic on Tuesday, but you're only responsible up to computing derivatives in this case. And yeah.